Welcome back to the deep dive. So, today we are staring directly into the abyss of the black box. And I don't mean that in a sci-fi Rise of the Machines way.
Right, no Terminators here.
Yeah, exactly. I mean it in a very practical, corporate, where did my data go kind of way, because we spend so much time celebrating what AI can do.
What it actually keeps.
Yes, exactly.
And it's the question that really keeps security researchers up at night. We have this assumption, right, that when we feed data into a model-sensitive stuff like patient records or financial ledgers, that it just gets digested.
Like it's gone.
Yeah, like it turns into abstract math, and the original data is effectively, well, just poof, gone.
Right. It's like tossing a sensitive document into a shredder. You have the confetti, the math, but you don't have the document anymore. But the paper we are unpacking today suggests that the shredder might be reversible.
Or, more accurately, that the shredder has a memory. And if you ask it nicely, it might just whisper your secrets back to you.
Which is a terrifying but very accurate analogy. So we are looking at a paper presented at the Network and Distributed System Security Symposium, NDSS 2026. The title is In Context Probing for Membership Inference in Fine-Tuned Language Models.
It's a mouthful.
It really is. Let's pause on the title for a second. In Context Probing. Membership inference. It sounds dense, but the implications are just massive for anyone who is fine-tuning a model on private data.
Absolutely, because the core issue here is that tension between utility and privacy.
Yeah.
Companies are rushing to fine-tune open source models like Llama or Pythia on their own proprietary data.
Right, because a law firm wants a model that knows its specific case history.
Exactly. Or a hospital wants a model that understands its specific patient demographics.
And the membership inference part, that's the actual attack, right?
Right. So a membership inference attack, or MIA, isn't about an attacker trying to steal the whole model. They don't want the gigabytes of weights. And they aren't trying to reconstruct the entire database from scratch.
It's much more targeted than that.
Much more. The attacker already holds a specific piece of information. Say, a leaked medical record for a Jane Doe. And they ask the model a simple yes or no question. Was this specific record used to train you?
Which is a huge privacy breach on its own, because if the model effectively says yes, the attacker now knows Jane Doe was a patient at that specific hospital.
And likely has whatever condition the model specializes in. It connects the dot between the person and the sensitive data set.
Okay, so how did we use to detect this? Because MIA isn't a brand new concept.
No, it's been around. And for years, the way we detected this, what we can call the old way, was by looking at confidence. The logic was really intuitive. If I feed the model a sentence and the model predicts it with, say, 99.9% confidence, it must have memorized it.
That makes total sense to me. I mean, if I memorize a song, I can sing the lyrics perfectly. I've never heard it. I'm just mumbling along.
Right. But here is the flaw, and it is the entire starting point for this NDSS paper. Some things are just naturally easy to predict, whether you've memorized them or not. If I say, the quick brown fox jumps over the duck.
Lazy dog.
Exactly. You are 100% confident in that. Now, did you read a specific document about foxes and dogs this morning?
No, it's just a super common phrase.
That is the confidence trap. A model might be super confident about a sentence because it was in the fine-tuning set, sure. But it might also be confident simply because it's grammatically simple, or it's a famous quote, or it just flows really well in English.
So the signal, I memorized this part, is completely drowned out by the noise of, well, this is just easy text.
Precisely. They call it a low signal-to-noise ratio. The old methods, like likelihood ratio attacks or loss attacks, they relied heavily on this raw confidence. And because of that, they suffered from poor generalization.
You just can't tell if the model remembers the data or if the data is just fundamentally easy. And I know there were some attempts to fix this, right?
Yeah, there were reference-based solutions where you train shadow models to compare against. But that is incredibly expensive and requires you to have access to similar data to build those shadow models.
And then there were reference-free methods, too.
Right. Things like min-k%, which looks at outlier tokens, or recall. But despite these methods, there just wasn't a principled way to separate, I know this because I memorized it, from, I know this because it's just plain easy text.
So the researchers behind this paper, they basically said, we need a better signal. We need to stop asking what the model knows because that's ambiguous.
Exactly. They pivoted to looking at how the model learns. And this introduces the core theoretical contribution of the paper, which is the optimization gap.
I really love this concept. It feels like we are moving from psychology, like what do you know, to almost physics. How much energy do you have left?
That's a fantastic way to frame it.
Yeah.
To understand the optimization gap, we have to talk about training dynamics and diminishing returns. Think about how a neural network actually learns. In the beginning, when the training starts and the model knows nothing about your specific data, it learns incredibly fast. You show it a few examples, and the error rate, the loss, just plummets.
It's like newbie gains at the gym. You just start lifting and you get stronger every week.
Yes, exactly. But as training goes on, you hit those diminishing returns. The improvements get smaller and smaller. Eventually, the model plateaus. It has learned pretty much everything it can from that data set. It's reached convergence.
So if a model has already been fine-tuned on Jane Doe's medical record?
It is at the plateau. It is a member of the training set. It has squeezed every ounce of optimization out of that record. If you tried to train it on that exact record again, nothing would really happen. The loss wouldn't drop because it's already at the bottom of the curve.
But if the model has never seen Jane Doe's record?
Then it is a non-member. Even if the model speaks perfect English and understands medical terms, it hasn't optimized for that specific sequence of words about Jane Doe. So there is a gap between its current performance and its potential performance.
And that is the optimization gap.
That is the gap. The researchers had this brilliant hypothesis. If we could somehow try to train the model on this specific sample for just one more step, the member wouldn't change much, but the non-member would improve drastically.
It's like studying for a test. If you've already memorized the textbook, you're a member reading a one-page summary right before the test doesn't help your score much.
Right.
But if you haven't studied at all a non-member, that quick summary causes a massive jump in your performance.
That's a great analogy. And they actually proved this empirically. They took a model, they ran just one single step of fine-tuning on a mixed batch of data, and they measured the drop in loss.
What happened?
For the records the model had never seen, the non-members, the loss dropped by a massive mean of 0.368. That is a huge sudden improvement.
It had a total aha moment.
Exactly. But for the members, the records it had already seen, the loss dropped by only 0.125, barely a wiggle. The model effectively said, yeah, I already know this, tell me something new.
Okay, this sounds like an absolutely perfect detection method, but wait. We have a huge practical problem here.
The black box.
Yes, the black box. If I'm attacking a model deployed by a corporation, say a customer service bot or a clinical API, I don't have access to the train button. I can't just run gradient descent on their servers.
Right. You can send text to the API and you get text back. Maybe get probability scores if you're lucky, but you definitely cannot tell their servers to update their permanent weights for you.
So the theory of the optimization gap is totally solid, but the implementation seems entirely impossible. How do they measure learning potential if they can't actually make the model learn?
This is the absolute genius of the paper. They found a way to fake the training. They use a technique they call in-context probing, or ICP, and it relies on a property of LLMs that we all use every day but rarely think about deeply.
In-context learning.
Yes.
But in-context learning, that's just giving the model examples in the prompt, right? Like, here's a tweet, classify it as happy or sad. Here's another tweet. Now do this third one.
That's the outward behavior, yes. But let's look at the mechanism under the hood. Why does that actually work? Recent theoretical research suggests that large language models act as meta-optimizers.
Okay.
When you provide examples in the context window, the model behaves as if it is updating its internal state to minimize error on those examples.
So when I give it a few examples in a prompt, it's basically doing a temporary, on-the-fly fine-tuning session.
Exactly. It is simulating gradient descent without actually changing its permanent weights. It's adjusting its attention mechanisms to fit the data you just fed it.
Oh, wow. So the researchers thought if in-context learning is basically a simulation of fine-tuning, maybe we can use it to simulate the optimization gap.
Spot on. And that leads to their attack framework, ICP-MIA. The goal is to see how much the model improves on a specific sentence after we give it a hint in the prompt.
Okay, let's break this down step by step for the listener. I'm the attacker. I have a leaked medical record. I want to know if the hospital's model knows it. What is my first move?
Step 1. You feed the record to the model as is, just the raw text of the medical record. And you measure the loss. How surprised is the model by this text? This is your baseline.
Okay, so I send the patient has a complex fracture in the left tibia. The model spits back a confidence score.
Step 2. You construct a probe. The probe is a carefully chosen piece of text that you paste right before the target record in your prompt. It acts as the context or the simulated training data.
So the prompt essentially becomes probe text followed by target text.
Right. And then comes step 3. You measure the loss on the target text again, but now that the model has seen the probe.
And we are looking for the difference between the two scores.
Exactly. We call it the ICP score. It's the original loss minus the loss with the probe. We are measuring the log likelihood improvement.
So if the score is really high, meaning the model got way better at predicting the text.
Then it was a non-member. The probe provided the context it was missing. It learned from the probe, it closed that optimization gap, and it performed much better.
And if the score is low, meaning the model's prediction didn't really improve at all.
Then it was a member. It already knew the information perfectly from its original fine-tuning. The probe was totally redundant. It's like whispering the answer to a trivia question to someone who already memorized the answer key. It doesn't help them score any higher.
That is so clever because it turns the model's own intelligence, its adaptability, totally against it. We are using its ability to learn from context as a weapon to reveal what it learned in the past.
It's a beautiful piece of judo, really. But as with all things in AI, the devil is in the details.
Right, the probe.
Specifically, what is the probe? Because you can't just put random noise or a recipe for pancakes in the context and expect the model to learn about a bone fracture. The probe has to be highly relevant.
And the paper outlines 2 distinct strategies for building these probes, right? Let's talk about the first one, reference database probing.
This is the more traditional, straightforward approach. You assume the attacker has access to a public data set that is somewhat similar to the private training data.
So if I'm attacking a medical model, I go out and download a public medical data set.
Right. The paper uses the example of iClinic, which is a big public database of medical questions and answers. If you are attacking a model that you suspect was trained on private hospital records, you search the public iClinic database for a record that is semantically similar to your target.
You find a match. Maybe not the exact same patient, obviously, but a patient with very similar symptoms or a similar diagnosis.
Exactly. And you use that public record as the probe. You're essentially priming the model. You're saying, hey, here is how a medical diagnosis usually sounds. Now look at this specific target record.
If the model hasn't seen the target, if it's a non-member, this primer really helps it orient itself. It says, oh, okay, we are doing medical syntax now. I get the pattern.
Right. It drastically reduces the surprise for the non-member. But for the member, the one who has already memorized the target verbatim, the primer is just unnecessary reading.
But the paper points out a pretty big limitation here, because in the real world, we often just don't have a public data set that matches nicely.
That is the distribution mismatch problem, and it's huge.
Yeah, like if a massive hedge fund trains a model on its proprietary, highly secretive trading algorithms, or a tech company trains on its internal Slack logs, there is no public version of that to use as a probe.
Exactly. If your probe is too different from the target, like if you try to prime that medical record using a Wikipedia article about sports cars, it just won't work. The attack fails because the probe doesn't help the model learn anything relevant to the target.
So they needed a method that works entirely in a vacuum, a method that requires literally zero external data. And the second strategy, self-perturbation probing, this is honestly my favorite part of the paper. It feels like magic.
It is remarkably creative. They just asked a simple question. If we don't have external data, why not just use the target itself to build the probe?
But wait, isn't that cheating? If I put the target sentence in the context and then ask the model to predict that exact same target sentence, won't it just copy and paste?
If you use the exact target without changing it, yes, that's trivial. Yeah. The model just sees the answer key sitting right there and gets a perfect score.
Right.
Both members and non-members would look like absolute geniuses, and you'd get zero signal. The gap disappears.
So you have to distort it somehow. You have to give it a fuzzy version of the answer key.
They call it perturbation. And they tried a few different methods for this. One was using a separate, completely distinct LLM, like a GPT-4 or a Quinn model, to rewrite the sentence. Paraphrase it, swap out some synonyms.
So the patient has a broken leg becomes the subject is suffering from a tibia fracture.
Right. And that worked okay. It was decent. But the method that absolutely crushed it, the one that performed best across the board, was shockingly simple. Masking.
Masking. Just deleting words.
Just literally deleting words. They take the target sentence, and they randomly replace a percentage of the words with a generic mask token.
So the sky is blue becomes the mask is mask.
Exactly. And they feed this holy Swiss cheese version of the text as the context probe. It acts as a fill-in-the-blank puzzle.
I have to ask, why does this work better than the smart rewriting method? Because human intuition would say a smart rewrite preserves the underlying meaning better than randomly deleting nouns and verbs.
It comes down to diversity and randomness. When you ask an LLM to rewrite a sentence, it usually gives you one very polished, very specific version. But with masking, you can generate dozens of completely different probes just by rolling the dice.
Ah, so you can attack the target from multiple angles.
Precisely. In one probe, maybe you mask out the subject. In another, you mask the verb. In another, the object. You create an ensemble of diverse probes.
And you are basically just looking for that one single probe that triggers the aha moment for the model.
Yes. For a non-member, maybe masking the verb makes the sentence super confusing, but masking the subject makes it suddenly click. By trying maybe 20 different random masks, you are maximizing the statistical chance that you find a cheat sheet that actually helps the model bridge that optimization gap.
Whereas for the member,
It just doesn't matter which words you mask. It doesn't matter if you give it a good hint or a terrible hint. It already knows the full sentence verbatim from its training, so its performance stays totally flat regardless of the probe. The optimization gap is revealed by the variance in how much those different masked probes help.
there's a Goldilocks zone here too, right? Because you can't just mask everything.
Correct. They analyze what they call the mask rate. If you mask too little, say you only hide 10% of the words, the probe is just too easy. It effectively gives the entire answer away.
So both members and non-members improve, and the difference vanishes again.
Right. And if you mask too much, say you mask 80 or 90%.
Then the probe is just mask, mask, mask. It's gibberish.
Exactly. It provides zero context. Neither the member nor the non-member gets any help from gibberish, so again, you get no signal.
So where exactly is the sweet spot?
The paper found it to be between 30% and 70% masking. In that specific range, the probe is informative, but incomplete. It's a genuine hint, not a full solution. That is exactly where the non-member struggles without it, and thus benefits greatly from the hint, while the member just breezes right through.
I find it so fascinating that just randomly deleting stuff is the state-of-the-art technique here. We always expect AI attacks to involve this insanely complex gradient mathematics or deep semantic analysis, but sometimes just adding random noise is the most effective tool in the shed.
It completely removes human bias. We aren't making assumptions about what parts of the sentence are important. We just let the statistics run and decide for us.
Okay, let's talk numbers, because the theory is elegant, but we need to see the scoreboard. They ran these experiments on models like LMA 3.2, Pythia, and they used data sets like Healthcare Magic, which is medical, and CNN Daily Mail for news summaries. How effective was this ICP-MIA attack in practice?
The results were, frankly, stark. Let's look at the Healthcare Magic dataset. This is sensitive patient-doctor dialogue. When they attacked the LMA 3.2 instruct model using that random masking strategy, ICP-MIASP, they achieved an AUC of 0.942.
0.942. Okay, for our listeners who aren't living in data science dashboards, an AUC of 0.5 is a literal coin flip. 1.0 is absolute perfection. 0.942 is basically, I can read your mind.
It is a devastatingly high success rate. It effectively renders the black box completely transparent. To give you some historical context, the previous state-of-the-art method, recall, scored 0.847. Another popular one, min-k%, scored 0.837.
So this isn't some marginal 1% improvement. This is a generational leap in attack capability.
It is. And it's not just about the raw accuracy either. In security auditing, we really care about the false positive rate. You don't want an attack that just accuses everyone of being in the training set. You want high precision.
You want the sniper shot, not the shotgun blast.
Exactly. So they measured the true positive rate when the false positive rate is fixed at a tiny 1%. On the CNN Daily Mail dataset, the old recall method caught about 19.5% of the members at that strict threshold.
Okay, so about 1 in 5, not great, but not nothing.
The new ICP-MIA method caught 51.8%.
Wow, it more than doubled the effectiveness. That is a massive difference in actual operational risk. If I'm a CIO deploying a model, that number absolutely scares me.
It should. But there is a finding in this paper that I think is honestly even more important than the raw numbers. It's a paradox that fundamentally challenges how the entire industry is building AI products right now.
The instruction tuning paradox.
Yes. In the AI industry, we generally differentiate between base models and instruct models. Base models are raw. They just autocomplete text based on internet data. Instruct models are fine-tuned to be helpful assistants. They answer questions, they summarize text, they follow specific orders.
And we all use the instruct models. Nobody chats with a base model unless they are a researcher debugging something. We want the helpful chatbot.
But the paper found that instruction-tuned models are significantly more vulnerable to this privacy attack than the base models.
Wait, let me make sure I'm getting this straight. The smarter, more helpful model is the one that leaks its training secrets faster.
Yes. And if you think deeply about the mechanism of the attack, it actually makes perfect sense. What does instruction tuning actually do? It teaches the model to pay close attention to the user's prompt. It optimizes the model to be a better in-context learner.
Oh, wow. So because we deliberately train the model to be a really good listener?
It listens to our probe. When we give it that masked context, the instruction tune model says, aha, the user's giving me a hint. I know exactly how to use this hint to improve my prediction.
It effectively studies the cheat sheet way better than the dumb base model does.
Exactly. The base model might look at the masked probe and just ignore it, or get totally confused by the masked tokens. But the instruct model knows how to extract value from it.
So the optimization gap just gets wider. The smart model improves massively on the non-member data because it's so good at learning on the fly. And that makes the difference between member and non-member blindingly obvious to the attacker.
It creates a really tough fundamental trade-off. We desperately want models that are adaptable. We want models that can learn from complex prompts. But this research essentially proves that the ability to learn from context is directly correlated with the inability to keep secrets.
That feels like a total trap. We are racing toward AGI, we're optimizing for a few shot learning and extreme adaptability, and in doing so, we might be systematically destroying privacy.
It certainly suggests that privacy by design and high utility are conflicting goals in the current transformer architecture. You just can't maximize both simultaneously.
Let's pivot to defenses, because if I'm that nervous CIO we mentioned earlier, what can I actually do? Can I use those parameter-efficient fine-tuning methods, like LoRa or QLoRa, because those are super popular right now for fine-tuning since they are cheap and fast?
The researchers definitely investigated this. They looked at LoRa low-rank adaptation. This is where you freeze the massive base model and you only train a tiny little adapter layer on top of it.
It's like putting a new lens on a camera instead of trying to rebuild the entire camera.
Good analogy. They found that the rank of the adapter really matters. The rank essentially dictates how many parameters you're allowing to change.
And I assume more parameters equals more danger.
Correct. As the rank increased, as they allowed the model to learn more complex patterns, the attack success rate steadily went up. The more capacity you give the model to memorize, the more it memorizes, and the more vulnerable it becomes.
What about QLoRa, the quantized version? That compresses the model data down to 4 bits. It makes the model a bit fuzzier mathematically.
That actually provided a small shield. Using 4-bit quantization acted as a natural regularizer. Because the model had less numerical precision, it simply couldn't overfit as sharply on the specific training samples.
So making the model slightly blurrier or dumber mathematically actually helped protect privacy.
It helped, but it absolutely didn't solve it. The attack was still highly effective, just slightly less so than on a full precision model. It's a mitigation strategy, but it's not a cure.
So what is the cure? Is there a silver bullet for this?
There is one gold standard defense, which is differential privacy, or DP, specifically DPSGD. This involves adding mathematical noise to the gradients during the training process itself.
We hear about this a lot in academic circles. It basically ensures mathematically that the model cannot learn any single data point too perfectly.
Right. If you train with strong differential privacy, say an epsilon value of 8 or 10, the attack completely collapses. The AUC drops back down to near 0.5. The model effectively hides the members among the non-members.
So if it works so well, why isn't everyone just doing this?
Because it comes at a very steep cost. Have you ever tried to use a language model trained with strict differential privacy?
I can't say that I have.
They are often, let's say, much less capable. The noise required to protect the privacy destroys a lot of the utility. The text generation gets worse. The reasoning capabilities drop significantly. Plus, training with DPSGD is computationally expensive and very slow.
So we are right back to the trade-off. You can have a perfectly private model or you can have a really smart model. Pick one.
Currently, yes. That is the harsh reality. And the paper notes that even when they used weaker differential privacy settings, the ones that preserve more of the model's utility, the ICP-MIA attack was still the strongest attacker on the leaderboard. It is the new benchmark that any new defense has to survive.
Before we wrap up, I want to touch on one specific scenario they tested that I think is crucial for the real world, the label-only access.
The OpenAI scenario.
Right, because most commercial APIs, GPT-4, Claude, Gemini, they don't give you the probability scores. They don't tell you, I was 99.7% sure of the word the. They just give you the final text output.
Exactly. They hide the log likelihoods. And since the optimization gap we've been talking about is calculated using those exact probabilities, the loss, you might think this attack is completely impossible in a commercial setting.
Security by obscurity. If I don't give you the raw numbers, you can't measure the gap.
But the researchers were one step ahead. They adapted the attack using a framework called PETAL.
How does that work without the math?
Instead of looking at the mathematical probability of the tokens, they look at the semantic meaning of the output text. They ask the target model to predict the target sentence. Then they use a completely separate betting model to measure how similar is the model's text output to the actual target.
So if the model outputs a sentence that means the exact same thing as Jane Doe's medical record, even if the specific words are slightly different, that counts as high confidence.
Exactly. They use semantic similarity as a direct proxy for probability.
It's like looking for a poker tell. Even if you don't show me your actual cards, the probabilities, the look on your face, the text output gives the whole thing away.
That's a perfect analogy. And the results show that ICP-MIA still works remarkably well in this setting. It outperforms the baseline PETAL method. So simply hiding the probability scores behind an API is not enough to stop this. The signal, the privacy leak, is deeply embedded in the language itself.
That is just so tenacious. It really feels like if the data is in the weights, this method can sniff it out.
It's because the method relies on something fundamental. It's not looking for a glitch in the software code. It's looking at the physics of learning. It exploits the universal truth that neural networks learn fast at first, and then they slow down. As long as that dynamic exists, this attack vector exists.
Let's zoom out and look at the big picture here, because this paper, presented at NDSS 2026, really seems to be a turning point. We move from looking at confidence, which was a messy, noisy metric, to looking at learning potential via the optimization gap.
And we learn that we can successfully simulate that learning using in-context probing. By creating a cheat sheet, specifically one made by randomly masking the target itself, we can measure exactly how much help the model needs.
If it needs a lot of help, it's innocent, a non-member. If it doesn't need any help at all, it's guilty, a member.
And the implications for the tech industry are stark.
Right.
We are in a massive race to build artificial general intelligence. We want models that can learn anything, adapt to any context, and solve any novel problem. We are spending billions of dollars to make models better at in-context learning.
We are optimizing for the very thing that makes them vulnerable to this attack.
Exactly. This research suggests we are on a collision course. The very mechanisms that make AGI possible, fast, adaptable, few-shot learning, might be fundamentally incompatible with perfect secrecy.
It raises a massive question for deployment. If you're building models, if I'm a law firm or a hospital, do I really want to fine-tune a model on my private files?
You really have to ask, is the utility gain worth the risk? Or should you look at architectures like RG, retrieval augmented generation, where the sensitive data sits in a secure database, not baked into the model weights?
RAG definitely seems like the safer bet after reading this. Keep the data out of the brain itself, let the brain be a general processor, and keep the secrets locked in the filing cabinet.
That is currently the safest architectural pattern for privacy. Because once the data is in the weights, you simply cannot guarantee it won't come out. The unlearning technology just isn't reliable enough yet.
So here is the thought I want to leave everyone with today. We are building these digital brains to be more and more like us, adaptable, quick learners, highly context-aware, but we also want them to be perfect vaults. We want them to lock away corporate secrets forever.
And as we know from human history, the smartest, most adaptable, most chatty people are often the absolute worst at keeping secrets.
Exactly. As we build models that are better and better at understanding us and our context, are we inevitably building the ultimate surveillance tool? Is a model that understands you perfectly, by definition, a model that simply cannot keep a secret?
That is the question that will define the next decade of AI security. The battle between utility and privacy is just getting started. And right now, utility is winning, which means privacy is losing.
A sobering thought to end on. If you're training models, check your data sets, seriously consider a graze, and maybe run some random masking tests to see what your model is leaking.
Definitely. Audit your models thoroughly before you deploy them.
Yeah.
Because if you don't find the leaks, an attacker armed with a method like this certainly will.
Thanks for diving deep with us. We'll see you on the next one.